4.5 linear approximations and differentials. So what I want to start with is if you're given a curve and we want to do some point, we know how to find the equation of the tangent line at that point. And if I went ahead and took some little box and wanted to zoom in and just wanted to focus on this, it would start looking like this as that point A. I'm still zooming in on that point A. If I want to zoom in again, I can see that maybe my graph of the function is getting closer and closer to being linear. And I could keep zooming in, keep zooming in. And this is what a linear approximation is. The whole goal is to realize that eventually that at this point A and the tangent line should be both linear. And if I have a function that, well, may not be a function that I can take the derivative of, because if I, at this point, if I go to zoom in on this one, I can see it's still a corner. Whether I keep zooming in or not, it's still a corner. So it may not be differentiable there. So how do I go about using linear approximation knowing this concept? So if I said that this point is A, I'm going to use A and f of A as a point that I want to find the equation of the tangent line. I'm going to use the derivative of f at A for its slope. So using point and slope, I'm going to find the equation of the tangent line, saying y minus f of A is equal to the slope, or the derivative of A, times the quantity of x minus A. And if I use this, I'm just going to go ahead and move my f of A over, and I get the equation y equals f of A plus f prime of A times the quantity x minus A. Normally we write this term behind in our, when we're solving, but for this situation, for linear approximation, this is the way it's set up. And it turns out in our definition, this is what the linear approximation formula is. And we're going to approximate values of A using this equation. So it's an approximation. Let's do some examples. If I'm given the function number 7, says use the linear approximation given in example 1 to answer the following questions. So they gave us an example 1 that we're going to use the approximation where I went ahead and converted it to this form so that I can write the approximation equation. So L of x. And we're going to go ahead and say when it was approximated near 0, that s of 0 plus s prime of 0 and then x minus 0 ended up being 60 minus x. This is from the textbook example 1. But our problem number 7 now says, if you travel 1 mile in 59 seconds, what is your approximate average speed and what is your exact speed? So we're going to use this equation, s of x for exact, and approximate with L of x. So if we want to find 1 mile in 59 seconds, approximate average speed, and because we were calculating this average speed at 60 miles per hour, and because it's really, say, we're going 59 minus this, we win a -1. So I'm going to approximate the linear function of -1. So I'm going to plug in -1 for x, and I get 60 plus 1, or 61 miles per hour. And then if I want to find out the exact mileage, I'm going to plug it into S of x. And I see that it should be plus a minus 1. So we're going to go ahead and say minus 1 to the negative 1. And it turns out to be 61.0. It's like 169. We'll round it to 0.017 miles per hour. So we have an approximate and an exact miles per hour when you're going speed at 59 fine air speed. So we want to go ahead and do example number 13. Given this function, 13 says we want to write the equation of the line that represents the linear approximation to the following functions at the given point A. We want to graph the function and the linear approximation at A, use the approximation to estimate the given function value, and then we're going to compute the percent error in your approximation using a formula that they gave us. I'll come back to that. So for here, in our function, first thing I'm going to go ahead and do is I want to find the linear approximation. Remember our linear approximation formula. So I'm going to go ahead, in order to plug everything into this equation, I'm going to need f of 2 for my first point. I'm going to need to find the derivative of the function, and I'm going to need to evaluate the derivative at 2 to find the slope. So if I go ahead and do that, f of 2, I should get 8. Finding the derivative of this function is negative 2x. And then finding the slope of this function at 2 should be negative 4. So I'm going to go ahead and plug into this linear approximation all my info. If I go ahead and simplify this expression, I should end up with 16 minus 4x. And then for part B, where it says to go ahead and graph the function and the derivative, really what I'm going to do is you could just quickly sketch both of them. So then if I move on to part C, it says find the 2.1, where it says f of 2.1. I'm going to use a linear approximation for that. If I plug in the linear approximation of 2.1, I've got 16 minus 4 times 2.1. Oops. So we see that an approximation is 7.6. So we could calculate what the actual is by plugging f of 2.1 into the original function using a calculator. But what I'm going to go ahead and do is for part D, they want us to use find out what the error is, percentage of error. So 100 because of the percentage. We're going to use the approximate value that we just found using the linear minus the exact, and we'll plug it into the calculator for the exact. And then it's the absolute value of that, and then it's all divided by the absolute value of the exact. So this is the formula for an error, and we're going to go ahead and evaluate this. So I would be plugging in. So I'll be plugging this into my calculator, f of the 2.1 in the absolute value function, and then absolute value. So I put everything in the calculator as 1 using the absolute values in my calculator and evaluating it with the function directly. So the 12 minus x squared. So in the calculator I had entered And then I got 0.13, and remember, because of the 100 it was percentage, so it's a 0.13% error on this. We can go ahead and always to determine if that's an acceptable error or not, depending on the application. I'm going to go ahead and walk through one more problem, number 27, and then we'll move on. Given this function, e the 0.06, we want to write a linear approximation equation, and we want to try to choose a value close for a that would be a good approximation. So all they're giving is this to us. So we're going to probably want to use where f of x is e to the x, and its derivative is e to the x. And we want to go ahead and choose a value close for a. So since it's 0.06, I'm going to go ahead and let a equal 0. So I need to evaluate f at 0, which is 1, and f prime at 0, which is 1. So we're going to go ahead and write a linear approximation using what we found. So f of a would be 1. Our slope, f prime of a, is 1. X minus the a, which is 0. And we get the approximation 1 plus x. If I want to go ahead and definitely evaluate what e to the 0.06 is, it's really 1.06. So without a calculator and trying to approximate this, we see that e to the 0.06 has a value of 1.06 approximately.